Good afternoon. This is Oliver Lewis from Tubi, and we'll be talking about parallelization of structured streaming jobs using Delta. So, the first thing that we want to talk about is what is Tubi? So, Tubi is an ad supported video on demand service with one of the largest online catalogs of free content. So, like Netflix, the bulk of our revenue is attributed to content recommendations that make personalized experiences for our viewers. To power up our recommendation engines, we continuously process a large streaming dataset of customer events. And I'll show you in a little bit like what these events look like. But roughly we get about 40,000 requests per second, which aggregates to about 800 million records per day. And in terms of our data size, that is equals to about 500 gigabytes per day. So when we are thinking about these events, we have like a pretty robust architecture to ingest these events. We get all these client events hitting our backend service, which then sends it to like a Kinesis queue, which then hits our enrichment service where they are joined with a lot of data sets. And then those data sets are finally ingested to from a consumer, Spark. So Spark was the way we have created the job is it's a streaming job that reads these events and writes it into our data lake. The initial problems that we had with that was that our event out here is an immutable event, right? We have the language semantic is that we have a person watching content. So this helps us make it very extendable. And the way we want to have is like an expressive vocabulary that describes a user action. So if you just go to another example, if you see this example out here, if you have like a person watching content on a platform, and that helps us design easily immutable events that can be changed and tweaked that will eventually reach our data lake and we can generate insight from them. When we have the pipeline designed like this, we have a trigger we have like a Spark that's running as a streaming job that has a trigger timestamp, and the trigger kind of like has issues with file sizing. Like we tend to have too many small file sizes, and this was something that we were always like facing a problem with, and we needed to find a better way to resolve that. I will show you in a bit like how Delta really helped us solve that problem. Another problem was data deletion process. So anytime we needed to make changes with that data, and we needed to like reprocess the data, we would have issues with like the streaming jobs managing the state, and we needed to kind of rerun the entire script all over again. Multiple streams writing to the same location. This was also not easily possible with the first version of structured streaming. That's just because we could not have the folders being updated at the same time. We had like a hacker way of like using separate checkpoints to maintain this different streaming jobs, but it still wasn't a very straightforward method. And that is something where we started using Delta. And Delta was, it came with its own set of features also that really helped us make our decision to, like, using Delta. The first thing that it solved was we were able to optimize the table and vacuum all of our S3 files without interrupting the streaming jobs. We also did not need to worry about the transaction consistency of Delta because long running deletes or changes to history were able to be done without impacting the streaming data coming in. And also, as most of you know, like with the GDPR and CCPA changes that are being done, like for most of the data deletion right now, we were able to support that using Delta just because of its transaction log capabilities. Another thing that I'd mentioned in the previous slide about not being able to run multiple jobs in parallel because of the Spark metadata issues that we had to deal with and consistency issues, we did not need to worry about that anymore because we get full-fledged transaction log capabilities using Delta Log. So that was another really good reason for using the entire for the entire transition into Delta. And this is actually where we start our presentation in the actual detail, because this is our example that we'll be using for the rest of this presentation. It's a real-time streaming session job which will trigger every 10 minutes. Let us imagine we have written this kind of like standard code, and we test it, we write all our unit tests, and we deploy it on production. Like everything works great, we are like content and there are no failures in production. The cluster size is right, we're able to like process records in a timely fashion, real time enough. But this job is still lacking something, and that is we do not like the business team is not able to get any kind of like historical reports, right? Because there's no comparative analysis being done for our data set. So now we need to figure out a way to backfill our data. And that is actually the main thing that we are trying to solve in a very structured and supported manner using Delta, because this was not possible with the first version of the way we had written our code, but it's kind of mm, easily supported with Delta. So let's talk about how we manage that with Delta. So when we're trying to strategize to do a backfill job, the first thing that comes to mind is let's write a batch job that would, do the to perform the backfill. However, writing a batch job would require a pretty major rewrite of our state management code, as I described earlier, right? Like our sessionization job is using stateful management, and if you have to rewrite this job into into like the batch mode operation, it would require us to rewrite all of that state management logic into a separate batch mode supported logic, and it would also require us to maintain two separate code bases. So this was actually one of our first constraints, to keep the job as a streaming job and not have to rewrite the business logic. So to keep the job as a streaming job, we would still need to figure out a way in which we can gracefully terminate the job on completion. Because as you know, like as most of you all know, with like streaming jobs, the only way to terminate a job is to receive some kind of like a termination signal, or like some kind of like a some monitoring signal that will say that okay, our job is terminated, we need to kill the job now. But luckily for us, like Spark gives us a useful method for doing this by using trigger at once, which will load the entire data frame, run the job, and then stop the stream on its own without us having to write special logic to terminate the job. There is one small gotcha moment out here, is as most of you all know, do not replace the read stream with a read and the write stream with a write, because implicitly flat map group with state is going to convert this map groups is going to convert it into a map group function, and you lose state management entirely. So that's just one thing you need to remember. There are issues in backfilling large data sets. For example, if we set the start date to 2016 1st of Jan and the end date to, let's say, current timestamp when we have started the job, there are a couple of issues. The first issue would be the job probably runs for a long time where it's like reading in a lot of the incoming data, and it starts executing the logic and the job fails. Uh, and that is something that we really do not want to do, because I mean that's going to be really annoying for us, right? Like we don't want a job to fail after 5 or 6 hours of running. Like if a job wants to fail, you'd rather the job fail right away than for it to like run for a long time and consume resources before failing. So that is one thing that we want to avoid. So you don't want to have a job that has a really large batch size. And I'm using the word batch size because I want to like elaborate on how we define an ideal batch size in a few minutes. The second thing, as you must have also noticed, is that I'm using state management in the stateful job that we are using with sessionization. And state management cannot hold such a large state. In fact, the job would fail much quicker. So, with that said, we want to think of finding the right batch size. So, we want to be able to encapsulate the data into something that is more easily sensible and more easily triggered and completed. So, when we are trying to identify a small batch size, we want to be able to encapsulate the data into a task that can be triggered, executed, and completed. Here, the key word to remember is like we should be able to get completed, because that will enable us to track the progress of the job. Since our data is partitioned by date, we decided to just keep like the granularity of a task at the date level. It is also important that the job is idempotent, at least on the task level and the date partition level, so that reruns of the same job will not cause duplicates in the output. Another thing that we also need to keep track of is that in case we set up a loop to execute a job, and if there's a certain failure within a certain task and we rerun it, we should not have like duplicates and or like any kind of like failures the in the final output of the batch run. So let's think about the next thing that we need to track about. It's performance. To make the backfill go any faster, our immediate intuition is to increase the size of the cluster. So let's take this example, right? The example on the presentation right now. The image out there is showing 3,886 tasks, and we have 64 cores. I'm just like giving you the cluster I ran this on. It was a 64 node cluster. So it took a 64 core cluster, and it takes about 8.2 minutes to run this job. So if we increase this cluster size to have 3,886 cores, we can actually complete this job in about 8 seconds. So our intuition that we had at the beginning to increase the size of the cluster was actually correct. However, there are a few caveats to this approach. If we increase the cluster any further, we start getting diminishing returns. And that's something that I'm also going to show in the demo in a little bit. But I also want to like talk about like, how we need to have a job running in parallel, but also make sure that our cluster size is at least intuitively correct. And the way I like to think about this is like the pizza problem. So I know it's a little funny, but like when I was trying to imagine this entire thing, I literally thought of like the pizza problem, where you have like a group of friends around you and you have four slices of pizza. What we have is like Spark is really great at parallelization. So all the four slices of the pizza are picked up immediately, but we are still going to have four hands that are idle because there's just not enough pizza. But if you look at the number of cores, it's always greater than the tasks, and you end up having like a large cluster that is not being fully utilized. Like if you look at this legend of this chart that I've zoomed in a little bit, if you look at the CPU, is it's averaging at about 29.9%, which is about like one third of the entire cluster. And if you look at the chart on the right, you can also see like spikes in the CPU usage. So that should be a good indicator for you to realize that maybe the cluster is being underutilized. Uh, and the reason for that could be that there are a lot of IO operations, and like in real world jobs, there are a lot of IO operations that happen. And IO operations are not CPU bound, they are IO bound. And IO bound operations might sometimes use less number of cores to run. So that ends up leaving a lot of idle CPU cores. So with that said, I then ran another analysis to calculate like for a single date partition, at what size do we start seeing diminishing returns? So this is a very arbitrary line that I drew out here. And you can see that anything to the left of the red line shows a pretty good decrease in the time taken for the job to complete, right? Like the rate of decrease is much higher. Whereas everything to the right of the line shows a slower slope, like a smaller slope in the decrease. And that's kind of like my assumption to show that where there is a diminishing return. So when I was trying to decide like a single node if I had to run a backfill on a single partition, I would spin up a cluster of 32 cores. So if you just do the math, if I'm running three dates in parallel, I would want to spin up a cluster size of 96 cores. And we'll see later on in the demo also, like how this kind of fares and like what are the outputs that we see in practice. Uh, okay, so let's move on to the next slide. And this is another metric on performance. When we're trying to design a cluster, when you're trying to design like a parallel job, you want to have like the number of tasks as they increase. You want them to increase in relation to the cluster size in a linear fashion, which means that at a certain threshold, if you increase the cluster size more, you want to make sure that more runs are running in parallel instead of just having like a block where things are not increasing in performance. And that is also with the next slide, where we're talking in backfill in parallel. So, as most of you all must have already got the context that I'm trying to run this entire thing in parallel. And the thing that I put a little importance on was that separating the business logic of the code from the execution logic of the code. So, when we do spend time with the execution logic of the job, we can also structure the job to be more performant in backfills. Another question that I frequently hear is that why not use a technology like Airflow or like a scheduler to handle submitting these multiple jobs? The quick answer for that I could think of is that you can actually set up a scheduler like Airflow to run these in separate environments, but just be aware that you'll need to set up monitoring for each of these jobs separately. And that is something that you also need to be tracking separately. Whereas in this approach, you can do it within the same context. So This was actually a funny quote. Well, not a funny quote, but it's a pretty nice quote that I read from Rob Pike, who is one of who has done a lot of work with the Golang programming language, and he states that concurrency is not parallelism. So even though we're using parallel collections to parallelize our work using while we're using Scala parallel collections to parallelize our work, and we have written a really concurrent job, that does not necessarily mean that the Spark is going to run this in parallel. And the reason for that is Spark uses a first in, first out scheduling strategy by default. So even though parallel collections launch these Spark jobs in parallel, but the Spark scheduler may not actually execute these jobs in parallel. So we want to move to another strategy, and that is by using futures and the fair scheduler pool. By default, each pool will get an equal share of the cluster, but inside each pool the jobs will run in a FIFO order. We can obviously tweak these parameters by changing the scheduler mode, the min share, and the weight depending on our strategies, but for our example in the demo we're going to be using the default. In this demo, I'll walk you through an example of structured streaming using FlatMap group with state, and we'll go through the different modes of operation using batch, parallel collections, and futures with scheduler mode. So let me show you the case class that we'll be using in this run. So the first case class is your input data, which is going to be for the input data being sent to the sessionization job. The next one is your session state, which is being used by the FlatMap group with state to maintain the state object. The next one is your output data, which is basically for the emitted records from your sessionization job. There are a few other case classes out here and variables, which I will explain. They're more like helper variables, which I'll explain when we use them. The next case class that I want to explain is actually being used specifically only because we're using a windowing function with trigger.once. And that's because when you do have a window function, there could be some sessions that are still active in the state store and have not been emitted out yet. So at the end of the trigger.once run, you want to make sure you use the SQL context to read the checkpoint location and the state folder. So you can read the open sessions that are still that should have been emitted but have not yet been emitted, because you want to make sure that they are added to the output. Just please make a note of that. That's pretty interesting and important and there's a good reason for doing that also. The next thing is your sessionization function. This is a really standard function shown in most books out there. It's that if a state has timed out, you want to make sure you remove that state and add it to the output iterator. Else, if the state exists, you want to update that state, or you want to create a new state if it does not exist. And the next steps would be to update the existing state with the new state variable and update the timeout timestamp. The next function that we're using is going to be your run streaming query. The run streaming query is using watermark, just as I mentioned, right? Like we're using watermark of 12 hours. So we need to use the state stored writer to flush out open records. We are also grouping by device ID, and we're using FlatMap group with state with the group state timeout as an event timeout, and we'll be passing the sessionization function to this FlatMap group with state function. We are also setting the trigger out here as to trigger.once. The next function is your run state stored query, which is actually going to be like a post query to the above function. The reason for using this is you want to make sure that you append all the open states that are in the state store to the same output location for each run. Okay, so now let's actually talk about the different modes of operation, right? And the first mode of operation is your batch mode. You can see that I'm iterating over 3 dates out here, the 1st, 2nd, and 3rd of May. And we'll be initializing the output folder. And this is just because of a eventual consistency issue in Delta. You want to make sure that you update the Delta log before you run the individual runs. Let's talk about the encapsulation within the dates out here. So if you notice, I'm using dates.map. So I'm going to be iterating over the entire collection of dates sequentially. And for each of them, I'll be running a pre-query step, which is going to delete the existing folder if it already exists. I'll be running the streaming query as step 2, and then I'll be running a post query step. The post query step, all these 3 steps are going to be run within for each and every date, right? So no matter which date is thrown at this function, I'm going to be running each of these three queries. So that also helps you visualize that, okay, if you notice that there's a pattern to your steps being run, you want to encapsulate that into a single function, and then being able to map over it gives you a good amount of control over how to parallelize it. And and I'll show you that in a minute, but let's check out the output of this run. I'm not going to run this just for time constraints right now, but if you look at the output of this run, you can see that each run is taking approximately 100 seconds, and the total run is about 318 seconds. So if you check this in parallel, the first things you'll notice is that I'm the only change I made was add a dot par to the dates collection, which changes this collection to a parallel collection. Everything else remains exactly the same. The only thing in the output is that now we can see that each of them are not running in the sequential order anymore. They are pretty randomized. And the time taken for each individual run is now much higher than 100 seconds. It's about 175 seconds. And that is because we are now looking at sharing the cluster between all the different runs. So it makes sense as to why it's higher. But if you look at the total time taken for the entire job, it's almost more than 100 seconds faster. And that's kind of equal to the slowest job in the run. So this actually gives you a very quick demo of like how you can increase your job performance significantly by running it in parallel. Although there are a few caveats to this approach, which I will discuss in the presentation after the demo, but let's move on to the next mode of operation, and that is using futures and scheduler pool. So I wanted to quickly give you an example of how we can change the level of parallelism in a concurrent job. So if you notice out here, by default, the amount of parallelism is equal to the number of cores on your driver node. So if my driver node had 8 cores, I'm going to get a parallelism of 8. But if you could change that, right? You could also change and tweak the amount of parallelism that you want in your job. And one way of doing that is by using this new fixed thread pool class or function and setting that to the execution context. So that gives you a good way of like changing it. Since in my job we have about 3 dates, I just set this to a value of 3. Of course, if you're using much larger clusters, you can change it to a more appropriate parallelism size that you have calculated. Okay, so I'm going to actually run this cell. So while this is running, I'm going to also give you a few things that I found pretty important. So in this, I'm going to encapsulate the about task in a future, and I'm going to be waiting for the result of the sequence of futures at the end. The other change I made is that I set the scheduler pool to the Spark context for each individual run. So each individual run is going to get its own separate pool. So that helps the run get a good amount of isolation from the other runs, and it's able to like split, and the cluster is able to split its resources for each of the runs. So while this is running, let's look at the Spark UI. If you look at the stages right now, you can immediately see that the fair scheduler pool has 3 more new pool names: pool 0, pool 1, and pool 2. And the min share, the pool weight, the scheduling mode are all defaulted to the default values. I haven't tweaked them yet, but you can obviously change them. Let's click this again. Yeah, and this is actually why I wanted to show you. If you look at the running tasks out here, they're all 32, 32, and 32, which is exactly what I described earlier, right? That we are able to evenly split the resources, split the cores between each of the runs. And that's something I found pretty useful if you have like some jobs that might be hogging resources. So if you look at the run out here for pool 0, it's a little ahead. Let's see if I can show you another part of the demo. So what I wanted to actually show you, it's taking a little time, but what I wanted to actually show you was that when pool 0 does complete, the resources held by pool 0, that are 32 cores, again get reshuffled between the remaining jobs that are still running. So that actually helps you accelerate to completion once a certain job has completed. It does not hold its 32 cores and not take in new resources when available. And I think that was something I found pretty nice and useful. And that actually completes my demo. I hope this was really informative and helped you get a fair understanding of how we can improve performance by making minimal tweaks in the code. Let's get back to the presentation, and we can further
our discussion.
Great. So as you guys have just seen in the demo, we ran this over a 96 node cluster, and we got a pretty good understanding of how we can run this in batch mode, parallel mode, and pool mode. Now let's take a look at the performance charts on different cluster sizes. So if you look at the chart on the left, it shows you that we see performance stabilization at 72 cores. In the case of parallel and pool, if we divide 72 by 3, we actually get 24, which is much lower than our initial assumption of 32, which is kind of like, remember the earlier assumption that I asked you guys to make with the arbitrary red line with 32. So in a real world scenario, when we are running this in parallel, we actually get a performance improvement on the 32 cores, which means that we could have actually spun up this job and seen a really good, decent performance, even with just a 24 node cluster for each partition. So if you multiply that by 3, that would be about a 72 cores, right? The next thing that we want to notice is the chart on the right. So the chart on the right shows you performance improvements across the board, but we do get like much higher performance gains at larger clusters, like clusters like 96 and 180. If you notice the difference between running this job on a batch mode versus a parallel mode, the parallel mode shows a significant jump in performance. Um, yeah, let's go on to the next slide. If you look at this slide, this was something that I brought up very early on in the presentation also, and that is failure and recovery handling. So we should be able to handle failures and retries within the job. So if you look at the three tasks that I've shown out here, right? The first task runs, it completes. And because we are having these jobs running in parallel, we are not easily able to track the progress of the job. So if a job starts and it fails, we're not able to easily track it. So we should have like additional state management set up so that we're able to monitor the state and the tracking in which the job is. With that said, please do look at our blog. We will have a working example with the GitHub links. Do check out our careers page. And if you have any further questions, do reach out to me on my LinkedIn or my email address. Thank you so much.